So my name's Kirsty Pringle. I work for an organisation called CMAC, which is based at the University in Leeds. And what we do within CMAC is we provide technical support to scientists that run complex models as part of their research. And one of the complex models that we support is the UKCA. And as part of that, I support or help to support people using the GLOMAP mode code within UKCA. So if it's something that you plan to use in your research, it might be something that you might need some technical support with at some point. So GLOMAP mode was developed at the University of Leeds. It was developed from a model called GLOMAP, and GLOMAP and GLOMAP mode were largely developed by Graham Mann, who's based at the University of Leeds. So what I'm going to do today is I'm going to talk through the design of GLOMAP mode and hopefully try and explain not just how it's designed, but why it's designed in that particular way. So when you come around to use it for your research, you'll be able to understand some of the motivation behind it. Should give you a kind of a clearer idea. So as I'm sure you know, aerosols are tiny, tiny little particles of either solid or liquid material that exist in the air all around us. They can either be natural or they can be formed as a result of human activity. And there's different types of aerosol in the atmosphere. And because UKCA is a global model, I thought it would be nice to start with a kind of global picture of the aerosol distribution. And this is an image that is produced by NASA. What they've done is they've taken satellite observations of the aerosol optical depth, and then they've used information from a computer model, similar to GLOMAP mode, but not the same, and they've used that information from the computer model to add a false colour to the image to tell you what these different types of aerosol are in the atmosphere. So they've identified 4 different types of aerosol. So you've got sea spray aerosol down here over the oceans, which they've coloured blue. You've got what they've called smoke or aerosol, which is in green here. The arid regions produce desert dust aerosol, so you've got this kind of orange plume coming away from the Sahara over the Atlantic. And then these white regions here are sulfate aerosol. So sulfate aerosol can be natural or it can be formed as a result of human activities. So the first thing you can see is that the global distribution of aerosol is something that's very complex. It's quite a hard thing to capture within a model. We need to in order for our model to be able to simulate this, we need to capture the processes which control and shape this distribution. And those are the processes which we've included in GLOMAP mode. So why would you want to model aerosol? It sounds complicated. Do we really need to do it? And actually we do really need to do it. And that's because aerosol have a huge effect on our climate and they affect a lot of the kind of features of the Earth system. So aerosol affect the climate in a couple of different ways. They're important for direct radiative forcing. Aerosol can both scatter and absorb solar radiation, which changes the temperature of the planet. They're important for indirect forcing, which is the interaction of aerosol particles and clouds. So aerosol particles are the seeds upon which cloud droplets grow. So if you change the number of aerosol particles in the atmosphere, then you can change the properties of these clouds, which in turn can change the temperature of the planet. So if that's something you want to research, then we would need to include that within the model. Aerosols are important for atmospheric chemistry because the aerosol particles provide a surface area on which chemical reactions can take place. They're also important in terms of biogeochemical cycles. There's a couple of different examples of this, but just as one example, aerosols can sometimes provide nutrients to nutrient-poor regions, which then has an effect on the biota and the emissions of that particular region. And finally, one of the more important and increasingly important effect of aerosol particles is that they can have an effect on human health. It's been estimated that 3.3 million people die each year prematurely as a result of exposure to air pollution, for atmospheric aerosol air pollution. And that's something which is obviously has a huge societal impact and is the subject of quite a lot of research at the moment. So it's something we might want to consider looking at within UKCA. So what I've done in this talk is that the way I'd like to do it is I'd like to so GLOMAP mode is a very complex scheme. It's quite a complex bit of code. And some of the design of the code isn't perhaps that intuitive, but it's been designed like that for a reason. So the way I've done it is I've tried to structure the code to explain not just how it's designed, but to explain the motivation as to why it's designed in that particular way. And to do that, I've identified 4 kind of key challenges. So 4 things that we would expect the code to be able to do, to kind of essential criteria that it needs to meet in order for it to be fit for purpose as a scientific model. So I'm going to go through these 4 challenges and then explain how GLOMAP mode has been designed in order to meet these challenges. And the first challenge in terms of what we would expect a code to do, how we would expect a code to simulate the aerosol distribution, is that observations have shown us that in any single air particle, every single air particle contains aerosol particles of a range of different sizes. So you can have particles which are just a few nanometers, so tiny little particles, clusters of molecules kind of hanging together, to quite large particles which are tens of micrometers in size. So we want our model to be able to represent this range of aerosol sizes. So this is an example of a measured aerosol size distribution. It was taken in China, but it could have been taken anywhere. What we've got is we've got size along the x-axis. Don't worry too much about the y-axis. It's just a kind of a measure of the abundance of the particles at that particular size. Each one of the coloured lines is a different season. And all I really want you to take away from this is the fact that in a single air parcel, a single measure air parcel here, you've got a range of aerosol of different sizes, which contributes to size distribution, and that size distribution is variable. So here the size distribution is shown to be variable in terms of season, because you've got this big winter peak, which isn't apparent in the summer, but you also get variation in aerosol size distribution due to location. So this is something we want to capture in the model. And in fact, we need to capture it in the model. We can't just make the assumption. So one of the key things of model design is when you identify complexity in the system, you need to ask yourself whether you need to include that complexity or whether you can just ignore it. Because if you can ignore it, you can simplify your model, the model will run faster, everybody's happy. But we need to include this complexity, and that's because the effect of the aerosol particles on climate and on health are dependent on their size. So it's these particles down here, these small particles, which have an effect on our health, because those are the particles we can breathe into our lungs. And it's these larger particles that have an effect on clouds. And these particles in the middle can all have an effect on the radiative scattering, so the direct radiative forcing. So we've identified a degree of complexity. We decided that we do need to include it in the model. And there's another number of different ways, or two different schemes, two different ways of representing the aerosol size distribution in models. The first is to use a sectional scheme. So what the sectional scheme does is you identify the range of aerosol sizes that you're interested in, and then you divide that range into a number of sections, size sections or size bin, and then you carry the number and the mass of particles in each one of these bins. This is a really good way of treating the aerosol size distribution, because it doesn't kind of make any assumptions about the shape of the aerosol size distribution. The aerosol size distribution is calculated almost from first principles. Unfortunately, the sectional scheme is too expensive to be included in a global model like UKCA. We actually have a version of GLOMAP called GLOMAP bin, but it's not been implemented in the UKCA because no one would use it. It would be too expensive to run. So happily we can use a modal scheme instead, and what the modal scheme does is it represents the aerosol size distribution using a number of interacting log normal modes. So here I've shown there's four in this particular example, there's 4 modes, and the modes can kind of overlap from each other and they can move. So in our scheme, the modes can move along the x-axis, so they can change in size due to the mass of particles within the mode, and they can change up and down in terms of the y-axis, so you can change the number of particles within the mode. And actually, just a number of interacting log normal modes, log normal distributions, is actually enough to reasonably realistically represent the aerosol size distribution. So we're able to recreate the kind of observational aerosol size distribution. We're able to simplify it down using a number of interacting log normal modes. So each mode has 2 prognostic variables, so 2 variables which are calculated at every time step in the model, mass and number, and computationally it's much cheaper than the more expensive sectional scheme. So the second challenge is that, as we saw in the first slide, particles can have a range of different compositions. It's not just singly an aerosol particle. You've got sea spray, you've got sulfate, you've got dust. So we want to carry this composition. We ask ourselves whether we need to carry this composition, and the answer is that we do, because the climate effects of the aerosol particles are dependent on the composition. So it's the soluble particles that are able to activate within cloud droplets, and not all of the species of aerosol particles are soluble. So we want to know what the aerosol is composed of, as well as knowing what size it is. And happily we can carry the composition of aerosol particles within a modal scheme. And the way that we do this is instead of calculating the total mass of particles per mode, we calculate the mass of each individual component of the aerosol per mode. So in our model we have a mode, we have these, so this is an example with 4 modes. So we calculate the total number of aerosols within those modes, and then additionally we calculate the mass of each species within that mode. So we have information on, for example, the mass of sea salt in that mode, the mass of sulfate in that mode, the mass of dust in that mode. And then if we want to know the total mass of aerosol in that mode, we simply sum the individual components. So there's two points to make, is that the composition varies between modes. So the composition of each mode is calculated. So the composition isn't set between modes, but the composition is uniform within a mode. So you can see that by these horizontal lines here. So within this mode, we know we have a particular fraction of that mode is composed of sea salt, a particular fraction is composed of black carbon. So within UKCA, we have a modal scheme. We represent the aerosol size distribution using a number of interacting modes. We can switch modes on, we can switch modes off. We can choose how many modes we want to use to represent the aerosol size distribution. The kind of best version of GLOMAP uses 7 interaction log normal modes. And these are split between 2 distributions. And the way that we do that is we choose to identify a hydrophilic distribution and a hydrophobic distribution. So this hydrophobic or insoluble distribution contains aerosol which don't take up water. So that contains black carbon and dust largely. And then we've got hydrophilic distribution, which contains aerosol which will take up water. And that contains all of the soluble species, including sulfate and sea salt. But it can also contain black carbon and dust, because once you have black carbon, if say you have an insoluble particle like black carbon, once it's mixed with some sulfate, then it becomes able to take up water, it becomes soluble. So you have your hydrophobic or your insoluble distribution, which just contains insoluble material, and then you have your soluble distribution, which is allowed to contain both soluble and insoluble material. So this is an example of the kind of output that you might get from any one grid box within the GLOMAP mode code. So I've tried to represent the 2 distributions here. So you've got these solid lines represent the soluble distribution. So you've got nucleation, Aitken, accumulation, and coarse soluble. And these modes are named according to convention. And the convention is that nucleation is the smallest mode is of a particular size, and then Aitken, accumulation, and coarse as you get larger. So this is your soluble distribution, and then your insoluble distribution. We don't have an insoluble nucleation mode, and that's because particles as small as nucleation mode are never insoluble, they're always soluble. So we can miss out that mode. But we do have an insoluble Aitken, accumulation, and coarse modes. So it is possible to run UKCA. I said that the best way to run UKCA is using a 7-modal distribution. Some people often run it with a 5-mode distribution, and the way that they do that is they switch off the accumulation insoluble and the coarse insoluble mode. And I'll explain a little bit about the kind of effects of that later. So each grid box of the model, if you're running the model, each grid box of the model contains information on the mass, the radius, and the composition of each of the 7 modes. So at any grid box in the model, you can pick out the information and you can recreate a simulated aerosol size distribution, which you can then compare to the observations. So there's 5 chemical species treated as standard within the UKCA. It treats sulfate aerosol. So sulfate aerosol is normally formed in the atmosphere as a result of oxidation of sulfur precursor gases, so sulfur dioxide or dimethyl sulfide. But it can also be directly emitted into the aerosol phase. We've got organic carbon, which is a kind of complex mix of organic species, which can be formed from biofuel burning or fossil fuel burning. Can also be produced as a result of biogenic activity. We've got black carbon, which is sometimes called soot aerosol. So this is this dark aerosol. It's able to absorb radiation. It's always formed as a result of combustion. It's formed a lot in biomass burning, these kind of large forest fires, but it's also formed from diesel cars. Sea salt and dust are both largely natural aerosol sources, which are formed obviously over the ocean and in arid desert regions. So this table summarises the standard setup of this 7-mode standard UKSAA aerosol scheme. So I've grouped these into these 4 soluble modes and these 3 insoluble modes. So you saw in the previous plot when I was showing the aerosol size distribution, the order of the size of the modes. The way that we keep the order of the size of the modes in the right order, if you like, is that we set boundaries onto each one of these modes. So the nucleation soluble mode has to have a mean radius of less than 5 nanometers. The Aitken soluble mode, the radius is allowed to vary between 5 and 50 nanometers, accumulation between 50 and 500 nanometers, and the core soluble is larger than 500 nanometers. So you can see that, and if a mode gets too large, for example, if you imagine you have an Aitken mode and it's about 40 odd nanometers and it's growing, then we're able to shift some of the mass from that mode into a larger mode, and that keeps the modes in approximately the right places. So we allow movement of mass of the aerosol between modes in order to keep the modes in more or less the right place. So you can, when you plot up the mean radius of the mode, you should see that they broadly lie within these boundaries. And then the insoluble modes, they have the same kind of size criteria as the soluble modes. So they lie on top of each other in terms of size, but they contain different species. So this is an example of the species which could be permitted within the modes. We could set it up so every species is allowed in every mode, but that would mean we would have to carry a lot of additional tracers. So what we do is we make some set some rules as to what's allowed based on our understanding of the aerosol dynamics and aerosol size distribution. Will we permit sulfate in the nucleation soluble mode? Normally, because it's only that's formed at small enough sizes for it to be permissible in there. Aitken soluble contains sulfate, black carbon and organic carbon. So this sulfate here could either be emitted at this size or it could be grown from this mode into that mode. Black carbon and organic carbon could either arrive in this mode because they're emitted into that mode, or because they're emitted into the Aitken insoluble mode and they've been able to age in the atmosphere and transfer into this mode. So you can see there's different pathways for species to get into the individual modes. So what we do is we set up a framework saying what's allowed where, and then the microphysics of the model allows those pathways to take place so the aerosols populate the modes. So accumulation and core soluble, the same, any species is allowed in the accumulation and the core soluble. Sea salt and dust are both allowed. Sea salt and dust are both emitted at quite large sizes in the model. So you've got sea salt can be emitted directly into the accumulation soluble or the core soluble mode. Black carbon and organic carbon, they can end up in these larger modes because they've been emitted into a smaller mode and they've grown into a larger mode. So they've gained material in the atmosphere, which has allowed them to move into a larger mode. The insoluble modes are actually a little bit easier because any growth or processing tends to move material from the insoluble into the soluble mode. So particles don't tend to stay insoluble in the atmosphere very long. There's processes which allow them to gain soluble material in the atmosphere and then they're transferred into the soluble distribution. So what's allowed in the insoluble distribution really just reflects the emissions. So black carbon and organic carbon are allowed in insoluble modes, Aitken insoluble, and then accumulation and coarse insoluble, you're allowed black carbon, organic carbon, and dust, because dust is emitted into the accumulation, the accumulation and the coarse modes. So I mentioned earlier, this is a 7-mode setup. I mentioned earlier that you can also run UKSA with a 5-mode setup. And the main difference between that is you turn off these 2 modes, the accumulation insoluble and the coarse insoluble modes, and you take out dust out of all this table. And in that setup, everything except dust is simulated in exactly the same way, but dust is, instead of being emitted in a modal scheme, dust is treated in a sectional scheme. And that's done for historical reasons because there's been a sectional dust scheme within the unified model for a very long time. So it's possible to just basically take dust out of the equation. You have it running in the background, so it's there for all the radiation that you might need, but it doesn't interact with the aerosol in any way at all in this 5-mode setup without dust. So depending on the science you want to do, the research you want to do, you have to make the decision whether you want to include dust here or whether you're happy to take it out and run the 5-mode scheme. So the final challenge, so we've got kind of a framework, we've got our modal scheme which is able to simulate aerosol size distribution, we're able to treat the composition of aerosols within the atmosphere. The final challenge is, well, the third challenge is that there's a lot of microphysical processes which control and change and shape the aerosol size distribution. And if we don't treat these within a model, we won't be able to correctly represent the distribution of aerosol throughout the atmosphere. So this diagram here summarises the kind of key processes which control and shape the aerosol size distributions. From a textbook, it's got that kind of textbook air to it. And it kind of shows the main processes. So you've got, the first one I'll talk about is emission, so kind of following on from Marcus and that. You can either have emission of gas phase species, so gas phase species which then go on to form aerosol in the atmosphere, or you can have the direct emission of aerosol particles. Then from these precursor gases, so this the gases which can go on to form aerosol through a process of nucleation, which creates tiny little ultrafine aerosols. And these aerosols can grow in the atmosphere through either two processes, one called condensation, one called coagulation, which produces larger aerosol particles. They can interact with clouds, they can be taken up with clouds. As I said, it's the kind of the seeds upon which cloud droplets grow, so these aerosol particles can be taken up into clouds, and then they can either be rained out, so that's a deposition, or they can be, if the cloud is not precipitating, they can be, they're kind of released back to the atmosphere when the cloud evaporates. So I'll go through each one of these processes and I'll explain just briefly how it's kind of treated within the model. So there's two kind of different ways of doing emissions within, well, there's two different kind of ways of doing emissions. So Marcus told us about this earlier. Most emissions in the model are just read in from files. So they're read in from these gridded NetCDF files. We use that for what we call offline emissions. So these are emissions which aren't calculated within the model. So we read in a number of files. We read in gas phase sulfur species files, so dimethyl sulfide, sulfur dioxide are simply just read in from file. So Marcus also talked about the kind of this notion of subgrid stuff that happens on a subgrid scale, which we can't really capture within a global model. And actually one thing that happens within the aerosol is that when you emit high concentrations of sulfur dioxide, sometimes you get this kind of very fast conversion to sulfate, which we don't really treat within the model. So what we do is we assume a fraction of the sulfur dioxide that's emitted to this gas phase is directly emitted in the particulate form. So it's a way of saying, like, we don't treat this complex process, this plume process. What we're trying to do is trying to capture the effect of that process. And to do that, we just assume that a small fraction of the emitted gas is directly emitted into particulate form. And then we have to make the decision as to what size we want to, so it's going to be an aerosol particle, what size of an aerosol particle are we going to emit it as? Black and organic carbon are directly emitted as aerosol particles. They can come from biofuel, fossil fuel or wildfires, and they're emitted into the Aitken mode. We do find there's some sensitivity of the results to the assumption to the size that we assume the emission occurs at. But that's a kind of known unknown in the model. So we don't know the kind of correct answer. We have looked at the sensitivity of the results to that. We have two online emissions calculated in the model, and these are calculated online because they are influenced by wind speed. So we want to be able to pick up when wind speeds are high that we have this increased emission. So sea spray is calculated as a function of wind speed. At the moment we treat accumulation and course, we emit into the accumulation and course modes. There is some research that suggests we should include Aitken mode sea spray, but we don't as standard yet. And then mineral dust. Mineral dust is calculated within the model using the Woodward scheme. I've said here, so it can be carried in bins or it can be put into the mode. You make the decision when you set up the model which you want to do. So nucleation. So nucleation is the process of new particle formation in the atmosphere. So semi-volatile vapours can kind of cluster together to form tiny little particles in the atmosphere. This is a really important source of particle formation. It's been estimated that 45% of the particles which are able to interact with clouds, particles large enough to interact with clouds, are actually formed in the atmosphere from nucleation. So they're not emitted into the atmosphere, they're formed within the atmosphere. So this is a process that we really need to include in the model. And there's two places in the atmosphere where nucleation can occur. The first is in the upper troposphere, where it's very cold, it's generally quite clean, so thermodynamically it's quite favourable to condense these tiny little, for these vapours to condense into these tiny little particles. Excuse me. This is a process which has been known for quite a long time. We've got two schemes in the model. You can choose which one you want to use, but simply by setting kind of logical switches within the model. And then we also have a scheme of boundary layer nucleation. This is now pretty much used as standard in the model, although it's a relatively kind of a slightly newer development scientifically. I've included this image here. It just shows a boundary layer nucleation event. So it's been observed that in the boundary layer, you often get kind of these bursts of new particle formation. So this plot here shows time, particle size, particle number, and you can see you've got this sudden increase in particle number, and they grow rapidly in size as a new particle formation event. So the next two steps are condensation and coagulation. What coagulation does is if you've tiny little particles in the atmosphere, they move randomly through kind of Brownian motion, and because they're moving randomly, if they're present in high numbers, they tend to collide together, and if they collide together, they tend to stick together. So then you go from a situation where you've got lots of little particles to a smaller number of larger particles. So it's an effective way of growing your particle. It doesn't change the overall mass of the system, but what it does is it increases the average particle size. And the good news is it can be represented numerically quite easily. It's just treated within a subroutine of UKCA. Most of these subroutines, they're all controlled by logical switches. You can turn them off if you choose to, but unless you would never want to, unless you're debugging the model for a particular reason. So they're all logically turned on. They're not controlled within the UMUI, they're controlled within the actual code, because it's not anticipated that a user would want to turn them off, because the model wouldn't represent the atmosphere if you did turn it off. Condensation. Semi-volatile compounds can preferentially condense onto the surface of pre-existing aerosol particles. Again, this doesn't increase particle number, but it does increase particle size. So it's an effective way of growing their particles. So you move from the smaller particles to the larger particles. So you can imagine your average mass of your mode is shifting along the axis. You've kind of got an increase in particle size. And these processes are important because, as I said earlier, particle size has an effect on the effect of the particles within the atmosphere. Okay, so the next process involves being taken up into clouds. So not all particles can act as cloud condensation nuclei. Not all particles will activate to form cloud droplets. It's only the largest of the particles. So imagine if you've got kind of a rising air mass and it's kind of expanding and cooling, about to form a cloud, then it's the very largest of the particles within this air mass that will have water kind of condense onto them, because it's thermodynamically much easier for water to condense into the larger particles. So this is my little aerosol population before cloud droplets. I've got a range of different sizes. I've activated into my cloud, and it's only these two big particles, these two particles here, which we're able to activate to form cloud droplets. And these are called interstitial aerosol particles. So they physically are in a cloud, but they're not activated to form a cloud droplet. So these guys here, because they have activated to form cloud droplets, they're basically aerosol in this big vast sea of water now, because cloud droplets are really big compared to aerosol particles. And soluble species are able to dissolve into this cloud liquid water. So if the cloud rains out, then it doesn't really matter. But if the cloud then evaporates, if it's a non-precipitating cloud, the cloud evaporates away. And what happens is that after your cloud's evaporated away, the particles which have acted as cloud droplets are different. They're now larger. They've grown by this process. So you have a preferential growth process. And this is important. You can actually see the effects of this if you look at the size distribution in marine regions. So this is called in-cloud processing, and again it's treated as a subroutine within the GLOMAP mode model. Obviously we've emitted aerosol, we've processed them in the atmosphere, we also need to deposit them, otherwise we'd get more and more and more. So there's four kind of categories, if you like, of deposition. 2 of these are dry deposition, so they don't involve rain or precipitation, and 2 are wet deposition. So the dry deposition, what happens is that if you have turbulent movement kind of in the model layer closest to the model surface, closest to the Earth, and then it will bring aerosol particles within the atmosphere in contact with the Earth, and then they can kind of stick to the surface of the Earth, and that effectively removes them from the atmosphere. So this is parameterized as a subroutine within the model. It's dependent on the size of the particles. Larger particles are able to dry deposit more easily. It's also dependent on the surface type, whether it's ocean or forest or desert. It changes like the sticking ability of the surface to take particles out of the atmosphere. I've included this in italics because it's not really a loss process. It's called sedimentation or gravitational settling. It doesn't remove particles from the atmosphere. What it does is that, like everything else, aerosols are subject to gravity. So if everything else was still, they would slowly sediment down from layer to layer to layer to layer. So it doesn't remove them from the atmosphere, but what it does is it makes them more likely to be in the lowest model layer where they can then dry deposit. So it's kind of a loss process, but not really. But it's tends to be treated in, well, it is treated in the same kind of area of the code as dry deposition. It's dependent on particle size because it's a gravitational settling. We have in-cloud, or what's called in-cloud or nucleation scavenging. So this is the subset of the aerosol population which we're able to activate to form cloud droplets. If the cloud then precipitates, then it's these clouds which are lost from the aerosol population. So this is a size-dependent scavenging process because it's just the larger particles that are scavenged away. So it depends on particle size and particle composition. And then we have below cloud or impaction scavenging. And what that is that if you're air parcel, you've got some aerosol in you and then it's raining above, then the raindrops shoot through that air parcel. If they collide with those aerosol particles, then they're going to be able to take them up into the cloud drop, into the raindrop, and then remove them from the air parcel. So it depends a little bit on particle size. The smallest and the largest particles are most likely to be scavenged, and it occurs in any model level below a raining cloud. So these processes are kind of included in the model. They're all controlled by logical switches. That's everything you need to do to build your own global aerosol model. I hope you can kind of go away and build your own if you want to. However, if you want to be used within part of something like the UKCA, then the last thing you have to do is you have to link it to other parts of the model. So you can see there's a lot of places where UKCA might interact with other bits of the model. I wanted to show this just so you have it for your handouts. I'm not going to go through it, but it's kind of an idea of the call sequence. So you can see each one of the, you've got UKCA air control, which it kind of is the main, kind of the control for the aerosol routine, and then UKCA aero step, which is the kind of the basic aerosol microphysics steps. And then hopefully you can recognize some of the names from the processes I just described, like impaction scavenging here, rain out is the dry deposition, including sedimentation. So these are all documented within the Unified Model documentation paper. But just to have an idea that that's the call sequence that occurs when GLOMAP mode is run. So GLOMAP mode links to the other parts of the model in a couple of different ways. One way is that if we're interested in indirect forcing, we want to be able to calculate cloud droplet number. And if we want to calculate cloud droplet number, we need to know the number of aerosol which are there. So this is work from Rosalind West, in which she's taken a scheme called Activate, which calculates the cloud droplet number based on the aerosol size distribution and some assumptions about the in-cloud updraft velocity. And actually the model is able to reproduce the global distribution of cloud droplet number fairly well. We've got high concentrations of cloud droplet number where we have high concentrations of aerosol in these kind of polluted regions here, very low concentrations over in the marine region, and they compare reasonably well with observations. Another one is there with aerosol optical depth. If you're interested in calculating aerosol optical depth, then obviously you need to know what the aerosol is behind it. So this is the RAD-AIR scheme, which I think you'll hear about tomorrow. So that calculates the aerosol optical properties, for example, in the scattering and the absorption and the radiative fluxes. So that was a really kind of fast run through of everything that GLOMAP mode contains. I hope you followed it. I just wanted to show one slide to show that so the UKCA has been a long time in development, but it's now a model which can be and is being used for research. Some of the research that we're doing on it at the moment is looking at the sensitivity of the model, the sensitivity of the calculated forcing within the model to uncertain parameters within the model. So here what we've done is we've calculated the radiative forcing for the time period from 1978 to 2008. So it's a bit different from the forcing that you might be used to, where you're kind of going from pre-industrial to present day. So this is kind of like a modern day forcing. So you can see that actually things have kind of got warmer in Europe and cooler here due to the kind of the emission reductions that have taken place in Europe due to kind of air quality concerns. But then you've had a lot of emissions over here in China, which has led to a cooling over that time period. But instead of just calculating this once, we've calculated this multiple times. And each one of the times we've calculated it, we've taken a slightly different setting of key parameters within the model. So we've done what's called a perturbed parameter ensemble with the model. And using a technique called statistical emulation, we're able to calculate not just the forcing, but the uncertainty of the forcing. So we can say how confident we are in our calculated forcing for any particular region. And then using a statistical emulation, what we can do is we can dive into that and try and understand which parameters within the model are contributing most to this uncertainty. So that's something we can focus on in the future. So just to conclude, UKCA mode is a global aerosol model. It normally uses 7 interacting log normal modes to represent the aerosol size distribution, although you can use 5. It's pretty state-of-the-art in terms of representation. There's other modal models that have a similar approach, which have been used for like IPCC assessments, CMIP, that kind of thing. So it kind of holds its own on an international stage. It treats 5 species: sulfate, black carbon, organic carbon, sea salt, and dust. The elephant in the room for us is nitrate, which it doesn't currently treat, but that's a kind of ongoing matter of ongoing research. The model setup, so you'll be given a model setup which is fine for most purposes, but it is flexible if you want to make some changes. So for example, you're interested in dust, you want to look at the sensitivity, you want to look at sensitivity to different types of dust. You could adapt it to have 2 dust compositions and treat those separately within the model. So there's scope to kind of make the changes and set it up as you wish. It treats the main microphysical processes which control the aerosol size distribution. There's nothing outstanding in terms of major processes which we don't yet treat. There's potential developments into how well we treat them, which is ongoing, but most of them are included. It's coupled to some parts of the model, but there is still some work to be doing, ensuring that everything is coupled all together, because you can imagine some of the couplings like a 2-way process, which isn't fully complete at the moment. But overall, it is a working model and it compares well with observations. It's been reasonably well evaluated with observations. So hopefully it's suitable for purpose, and hopefully that you can use it within your own research. I made it through, thank you, like coughing too much.